Okay, so our next thermodynamic process is called an isotherm. And isotherm is a process that happens at constant temperature. So usually these happen relatively slowly and with the system connected to a thermal reservoir. So isotherm, constant temperature. Now, we're going to find the work done. So we have a force here that's, say, compressing our gas. And we know that the work done is minus integral P dV. Excuse me. So I'll just rewrite that again down here. But for an ideal gas, we can, of course, replace the pressure with nRT over V. And then the nRT comes out because, of course, we're an isotherm, we're at constant temperature. And you'll recognize this as being natural logarithm, and we're going to integrate from initial to final. So we've got minus nRT ln of V from final to initial. That'll be ln V final minus ln V initial. That'll be ln V final minus V initial. So that's how we'll find the work. Now, for an ideal gas, we've seen that the internal energy depends only on temperature. So, if the temperature is constant, then so is the internal energy. That means, of course, that there's no change in internal energy in this thermodynamic process. That means, if we apply the first law of thermodynamics, that there must be an exact offset between the work done and the heat flow in an isotherm. So to summarize then, first of all, let's say if we're compressing the gas and doing work on it, that's work in, or positive. That means thermal energy would have to flow out and be negative in order for the internal energy of the gas to remain fixed. And then if we allow work out, say the gas to do work, the work out is negative, then thermal energy will flow in, and in is positive, again, to ensure there's no change in the internal energy of the gas. So overall then, for an isotherm, delta U is 0. The work done, we just showed through the integral P dV, negative P dV, is minus nRT ln of Vf over Vi, and the thermal energy flow Q is just going to be the opposite of the work by the first law of thermodynamics. So that's a quick summary of isothermal processes. Now, for an isotherm, we can apply the ideal gas law as we did earlier, and we'll get nRT, which is a constant, over V. We see that this is proportional to reciprocal of volume. So pressure is inversely proportional to volume. This is a hyperbolic shape, a 1 over x graph, and there'll be a symmetry line here. So the graph is going to look something like this 1 over x graph. I don't know how good my symmetry was there, but you've certainly been graphing 1 over x for a long time, and so should be quite familiar with it. So a good way to get an isothermal process is to take this reservoir and to dunk it, say, in an ice bath, and then to make changes relatively slowly. So if we started adding some weights to this piston, bit by bit by bit, then what's going to happen? Well, we're doing work on the gas, so that's work in, so that's positive. What's going to happen is the gas is going to warm up a little bit, and there'll be heat flow out of the gas that will be negative. Now, if you were to take some little weights off the top and allow it to expand, then the gas is doing work, and so that's work out, that's negative. That's going to cool the gas a little bit, and then thermal energy will flow into into the gas from the thermal reservoir that it's sitting in. So it's sitting in a bath here to keep it at constant temperature. And so thermal energy will flow in, and that's positive. And we'll do that demonstration in class. So that's how you can maintain an isotherm. But the changes have to be relatively slowly just to allow the work done to be balanced by the flow of thermal energy, because that flow of thermal energy takes time. So it takes the system a little time to catch up to any changes. So you have to make them relatively slowly. Okay, so here's an example. This is actually a full thermodynamic cycle, and the answers are given here. Okay, so this is what you're trying to show. So first we'll sketch it in the PV plane. So we're going to have here's our pressure axis, here's our volume axis. And so what happens? So we start at a certain point, volume's 2 liters and the pressure's 400. Okay, so on our volume axis, I'm going to start right here, and then I'm basically going to be doubling volumes and doubling pressures. So I'm just sort of scaling those 1, 2. So here's a volume of 2 liters, and we're up here at the larger pressure, 400 kPa. So that's point A. That's an A. And then state B is twice as much volume, but half the pressure. So I see there's inverse proportionality. And then state C is this point right here. So if we go from A to B, sort of foreshadowing here a little bit, along a hyperbolic path, and then B to C along a straight line, and then C to A along a straight line. Our task is, first of all, to name those 3 processes. Then we want to find the temperatures and show that those are the 3 temperatures for A and B and C. And then we want to find the work done for each of those 3 processes, the thermal energy transfer, and the change in internal energy. So pause the video for a minute and work that out and confirm these results. Then when you're done, if you want, you can play back through the video and watch my solution to check. So just pause it right now. Okay, so if you're still watching, that's because you want to watch my solution. So first of all, we need to find the temperatures using the ideal gas law. So that'll be PV over NR. So for our point A, we're at 400 kilopascals. Sorry, 400 kilopascals, which is 400,000 pascals. The volume is 20 liters, but a liter is 10 to the minus 3 cubic meters. So SI units are pascals and cubic meters. And we use the ideal gas constant, the joule per mole Kelvin version. And of course, this was 2 in units of moles. Okay, so this works out to 48.11 Kelvin, and that'll be the temperature at both A and at B, because at the point B, the volume is doubled, right? You're going to have twice the volume of A, but the pressure has been halved. So you see that the 2's just cancel out, and it's the same ratio as the point A. Temperature C we can also do proportionally. At the point C, we see we have the same volume as at the point A, but the pressure is halved. So we see we're going to end up with a factor of a half there. We'll have exactly half the temperature at point C that we had at point A. So that's 24.005 Kelvin. So that's what we were asked to show, first of all, those temperatures. Now, clearly the process from A to B is an isotherm. It's happening at constant temperature. That's just by definition. And so we're asked to find the work, the thermal energy transfer, and the change in internal energy. Well, our starting point will be the change in internal energy, because we know that internal energy only depends on temperature. That means you've got to have the same value of internal energy here because the temperature is constant. That means it's not changing. That means that the thermal energy flow Q and the work done on the gas W are offsetting each other. Now, the one that we can find easily is the work, because work is integral P dV, but of course, pressure is nRT over V, and then temperature is a constant, so it gets pulled out. And as we saw, this is a log. So this will be the ln of the initial volume, final over initial volume. Okay, now I just went through that derivation again, just because it's always good to start from first principles. All right, now, the final volume at the point B, because we're going from A to B, just let me pause here for a second to check something. Okay, that's going to work. So it's going to be minus N is the number of moles, R is the ideal gas constant rather, T is the temperature of A and B, which is 48.11 Kelvin. Then we're going to have ln, natural logarithm. Now the final volume is exactly twice the initial. So that's going to be 4 over 2, that's just 2. Now ln 2 is positive, so this expression is overall negative, and the answer works out to 553. Okay, so then if we substitute, and that'll be in units of joules, then if we substitute into the first law of thermodynamics, since the work done is negative, Q must be positive 553. So there was work out, but there's thermal energy transfer in. That's how you get a isotherm. Okay, the next step in our process, we've done the isotherm from A to B. Now we're doing this straight line. Well, that's a constant pressure. That's an isobar, an isobaric process. Now, we can find the work done very easily there. It's integral P dV, but in an isobaric process, the pressure is constant, so it just comes out. So we're going from, this is a volume, not a temperature. So we're going from our volume of 4 liters down to our volume of 2 liters. So the volume's actually decreasing here. So this is going to be minus pressure, it'll be V final minus V initial. And so substituting in, it's going to be, the pressure is the constant value of 200 kilopascals. One more. Our final volume was 2 liters, so that's 2 times 10 to the minus 3 cubic meters. And our initial volume was 4 times 10 to the minus 3 cubic meters. And I should put the units of pascals in here. Okay, a pascal times a cubic meter ends up being a joule, simply because a pascal is a Newton per square meter. So when you multiply by cubic meters, you get Newton meters, which is joules. Now, this is negative, so we end up doing work on the gas. So work is in. That makes sense because we're actually compressing the gas to a smaller volume. Now, how do we find the thermal energy flow? Well, for an isobaric process, we can use the constant pressure specific heat. So we have 2 moles Cp is given as 20.8, and notice we're using the molar version. It's more common to use that in thermodynamics. And then delta T, so this is going to be final minus initial. And the final point, we end up at the point C. So this is going to be temperature C minus temperature B. So temperature C is 24 Kelvin. Temperature B is 48 Kelvin. So we see that the thermal energy flow ends up being negative. That means that thermal energy has flowed out of the gas. Now, the overall change in internal energy is the sum of those two. So 400 minus 998, it's minus 598 joules. So overall, this gas has lost internal energy. That makes sense, of course, because the temperature's gone down, and we know that U depends on temperature only. Let's do the last step in that thermodynamic cycle. So we've done the isotherm, we've done the isobar. Now we're going to do the constant volume pressurization. That's an isometric process, a constant volume of 2 liters. So the work done is easy because there's no volume change. We're not doing any work on the gas. So what's happening is there's some heat flow into it that's warming it up. And because this is a constant volume process, we have to use the constant volume specific heat. That value is given as 12.46 joules per mole Kelvin. And then final minus initial, so this will be temperature A minus temperature C, we're warming it up from 24 to 48 Kelvin. So the amount of heat that flowed into the gas is 598 joules. So when we apply the first law of thermodynamics, because the work done was 0, we find that the internal energy is increasing by 598 joules. So if we look at the overall process then, all 3 steps, now, clearly, we're ending up back at the same point, right? So there was no change in internal energy here, and I'm looking at the last column in the results chart. Here we lost 598 joules of internal energy. Here we gained 598 joules of internal energy. So overall, there's no change in internal energy for the process. And that makes sense because you're ending up at the same point, you're ending up at the same temperature that you started off at. Now, what about work done? Okay, well, from A to B, I guess we can call this sum of the work, or just call it work, because it's the total work done in the cycle. So for the overall cycle, so first of all, from A to B, work was out. The gas did work as it expanded. Then, from B to C, work was in. Work was done on the gas as it was compressed. Then, going back from and doing the isometric pressure increase, no work was done because there's no change in volume. So overall, work was negative or out, or work was done by the gas in this process. Now that's a good thing. That's what you want in a thermodynamic cycle. You want it to do work, say, moving your car tires or spinning the blades in a turbine. This is kind of the main, I suppose, this is what thermodynamics is all about, ultimately, right? Is getting some sort of thermodynamic fluid to do something useful for us. So work overall was out. And that's fairly typical. How about the thermal energy transfer? Well, first of all, we had positive thermal energy flow into the gas in the isotherm. Then, in the isobaric process, we had negative thermal energy flow out to the environment. Then in the isometric process, once again, we had thermal energy flow in, or positive. Overall, we had 153 joules positive heat flow into the gas. So it's overall in. Now notice that this makes sense, right? Overall in the process, you had 150 joules of thermal energy that flowed into your gas, and then the gas did 153 joules of work. Overall, there's no change in internal energy. But you used heat to do some work. And that's what thermodynamic cycles are all about. So that's an isotherm. In the following pages, there's some thinking interpretation questions for you to work on. Prior to coming to class, please think about these. So here's the first one. And it's just a PV diagram. It's just asking you to rank temperatures. Here's the second one. And this is asking you, when you pull out the pin, if this drops, what happens? And then at that point, you're done and ready for our next class in thermodynamics.